Welcome everyone for the second session of this afternoon. So this session is about practical attacks, and the first talk will be given by Adi Shamir, and it's about a new method to extract neural network models.
So first of all, I would like to point out that in this project, I cooperated with a wonderful team of researchers from TII in the United Arab Emirates. So it's probably the first official cooperation between Israeli and Emirati researchers. Something inconceivable just a few years ago. Okay, I don't have to tell you that companies are spending literally billions of dollars on training deep neural networks, and then they basically allow the public to interact with those networks by giving inputs and providing outputs while keeping the model itself as a black box. And the question is it a secure practice? Can you extract or steal or interpolate, call it anything you want, the model by interacting with it sufficiently many times? And specifically, we'll be interested in how many queries and how much time is required in order to try to extract all the weights of the network from input-output pairs. This problem had been studied for more than 30 years, and there had been dozens of papers published on it. I'll just give you an example from 1993, when Ron Rivest and Avram Blum showed that in the known message attack model, in which somebody is giving the adversary pairs of input and outputs which are not chosen by the adversary, but only dumped on him, then the problem is NP-complete because you can encode a kind of subset sum problem with very carefully chosen inputs and outputs. And we will be interested in the more realistic chosen input attack, in which I, as an attacker, can choose whatever input I want to give to the network, and I get the associated output. So the best previous result in this model was shown actually in Crypto 2020, when Karlini, Jagelski, and Mironov presented an algorithm which required a polynomial number of queries. But unfortunately, the analysis of the polynomially many answers required some kind of exhaustive search, and therefore it was polynomial query but exponential time. And the question is, can we do better? And the new result that I'm going to present here is that I'm going to show you how to extract all the weights from a black box network using a polynomial number of queries and a polynomial amount of time. We are going to introduce 3 new techniques in order to achieve it, but I'll probably have time to describe only one of them here. And we have experimentally verified it, and we worked on a realistic model with thousands of neurons and millions of parameters, and we applied the thing that required exponential amount of time in the previous paper in about 30 minutes on a strong parallel computer. How do the deep neural networks look like? Most of you have probably seen it. There are a bunch of numbers in the input, and then there is an affine mapping, which linearly mixes it with coefficients, which are called weights. It's an affine, so you also add free terms, which are called biases. And then each one of the outputs of this linear mixing is going through a ReLU function, and the ReLU maps one real-valued input to one real-valued output. If the input was negative, it outputs 0, and if the real-valued input was positive, then it just outputs the same number. And you go through several such steps, and then you provide a bunch of output numbers. In classification, it's usually your confidence level, whether the input was a dog or a cat or something else. Now I want to point out something that most people do not realize, and this is the cunning similarity between deep neural networks and block ciphers. So I put them side by side. Both of them operate by going through layers. In both cases, you have a linear mapping which is global, and then a bunch of nonlinear operations which are local. ReLUs in one case and S boxes in the other. In both cases, the nonlinear element is completely known because it's a ReLU, everyone knows how ReLU operates, or an S box. And the secrets, in the case of block ciphers, is some subkey which enters the linear part, and in the problem that we are facing, the secret are the parameters of the linear mixing. The main difference is that on the left, the inputs and outputs are real numbers, and on the right, they are bits. But you probably see how close the two models are to each other, and therefore, not surprisingly, we will be able to use techniques that we have developed in block cipher cryptanalysis into the new model, and that's how we will get our result. Okay, in this talk, I'm going to make all the possible simplifying assumptions. We know how to overcome all these limitations, but I don't have time to describe to you the complications. So I'm going to talk about plain vanilla deep neural networks, which are just fully connected networks with ReLUs. Known architecture, so there are R layers, each one consisting of the same number D of neurons. I'm going to assume that the neuronal weights and biases and also the inputs and outputs are all infinitely precise real-valued numbers, and that operating on infinitely precise real-valued numbers takes unit time. In reality, in our attack, we used 64-bit arithmetic, and it was good enough. But if you are dealing with finite precision, you have to go through a very complicated error analysis, how errors are accumulating throughout the computation. So I'm going to ignore it by saying we work with perfectly precise numbers. Now, there is one point which is very important, and this is that you cannot hope to get exactly the original set of weights, because there are symmetries which make different sets of weights behave functionally exactly in the same way. So if you look here, suppose that I multiply all the coefficients in this part of the affine mapping, all the weights and the bias by some number C, which is positive. The output will be also multiplied by C. And even though this is a nonlinear function, it is multiplicatively linear when multiplied by a positive number. Why? Because if the output was negative, and the output of the ReLU, if the input was of the ReLU was negative, and you multiply it by a positive constant, it remains negative, so the output remains 0. And if it was positive, then of course you have linearity because it just copies the input to the output. So I can go through this nonlinearity if I multiply all the coefficients by C, and I have to compensate by each one of the neurons in the next layer having the weight which is only connected to this particular neuron divided by C. Then you have no hope of distinguishing between the case in which I multiplied some of the coefficients by the number 5 in certain layer and compensating by dividing certain other coefficients in the next layer, multiplying them by 1/5. Okay, the attack I'm going to present, and also the attack that Carlini presented at Crypto 2020, is trying to find a layer, then peel it off, and then find the next layer and peel it off, etc. There are complications due to the fact that the mapping represented by a certain bunch of layers is not invertible in general. So at the point in which I'm going to describe to you how the attack works, I assume that there are a certain number of layers which I've already found. So there is an input function which is completely known. Then there is an output function of all the layers after the ith layer, which is totally unknown. And I'm going to describe to you now how to find the parameters in the linear mapping here, followed by the ReLU. So this is the situation. And our tool is the analysis of critical points. A critical point in the input space is defined as a point in the input space in which the input to some ReLU is exactly 0. So as I go in a certain direction in the input space and cross a critical point, a ReLU switches from being negative to being positive, or from being positive to being negative. And in the vicinity of any other point, non-critical point, the network actually behaves in a very local way as an affine mapping. So it is only the ReLUs switching sides which suddenly changes the behavior from one affine mapping to another affine mapping. And here is the input space. And the mental image you should have is that it is divided into cells. Within each one of the cells, the mapping is completely linear or affine. And if I go from any point x1 to any point x2, I'm behaving in a linear way until I reach a critical point where some ReLU switch sides. And then I get into a cell which represents a different affine mapping. And again, I have exactly the same mapping here until I cross another critical point, and so on. And typically, when you go between two random images in the input space, you go through thousands of ReLU transitions. Can you notice that you have gone through a ReLU transition as you go from x1 to x2? The answer is yes, because now the problem becomes a mapping from one input to say, I'm looking to one output, for example, the first one of the several outputs available. So the function looks like, as I go within the first cell, the first output increases, and then one ReLU switches, and as a result, the slope changes, and then I reach another ReLU switching, so again, the slope changes, etc. So you can easily identify those critical points by watching how the output changes as I'm going in a linear way through the input space. Now, consider a critical point x0, which is associated with a ReLU located at layer I. The important thing, and here all the stars align, the value, the output value, depends on all the layers. Each one of the layers is going to influence what is the output coming out of the network. The only thing I can see. But the locations I just calculated for where the critical point is located is when a ReLU at layer I had an input which is exactly 0. This is not influenced by anything which happens later on, in later layers. And as a result, the location is going to depend only on earlier layers, which are known. So that's a crucial observation. So the next step is to define the notion of a signature, something that characterizes a neuron, because whenever there was a critical point, I know that something changed, but I don't know which ReLU switched sides. So let's assume that the neuron that switched sides had this kind of affine definition. The x's are the inputs from the previous layer, and the c's are coefficients. I told you that you can multiply all the coefficients by the same positive number, and therefore I can, assuming that C1 is not 0, I can divide all the coefficients by C1, and therefore I get characterization of the neuron based on the ratios between the ith coefficient and the first coefficient. Now, notice that this is, in some sense, losing two pieces of information. One of them is the multiplicative constant, and that's okay to lose it because I have no hope of recovering it. We said that there is a complete symmetry of multiplying in one layer and the between two coefficients. I lose something else. I lose the sign, because the real set of coefficients could be either a particular sequence or the minus of all those numbers. And when I look only at the pairwise ratios, the sign disappears. And therefore, I know in this formulation, if I get the signature, I know how the linear hyperplane where the ReLU switches sides looks like. I'll show you in a moment how I calculate it, but I don't know if the positive side is on the left or on the right. I don't have the sign information. Okay, so the actual set of coefficients could be either this or that. And this was the source of the exponential analysis time in the Carlini et al. Paper. The fact that they had to guess which one it was. Okay, finding ratios between two coefficients is very easy. Suppose that I'm at a point on the critical, this is a critical point, so there is some ReLU which has just been crossed. I go, for example, in the direction of the first coordinate increasing. I go a very small distance. I move away from this criticality. Now I'm not critical anymore. And then I change another one, x2, for example, by a small amount, either upwards or downwards. And I have an oracle which tells me that I reached criticality again because this is where the output function changes direction. So remember, I have an oracle for being on the critical hyperplane. And the ratio between the size, how much was the tiny movement in x1 direction, divided by how much was the movement in the other direction, is telling me the ratio between the two, Ci divided by C1. Okay, so I can calculate for each one of the neurons its signature. And now the question is, how do I know where is this ReLU located in the deep neural network? If it is located among the first I -1 layers, which, as I assumed, I've already calculated, and I know exactly what are the ReLUs there, I'll check that indeed the new signature was one of the signatures which are already recognized, that I know about from the previous layers. But if it is not, then I have to go beyond, and let me very quickly go over it. Basically, if the same signature occurs multiple times at different locations in the input space, then it is likely to be in the current layer. And if it occurs only once, not repeated, it means that my analysis of the input function was wrong. At each part of the input space, I was using a different, incorrect input function. Okay. So the main difficulty now, and that's probably the last thing I'm going to mention, is how to find the sign of the neuron, whether the left side is where it was positive or negative. Without knowing it, I will not be able to give you the correct definition of the input function and be able to peel off the next layers. So here we introduce a new technique which we call wiggle. And the idea is that I'm going to wiggle the input in a certain direction, carefully chosen direction, just like in differential cryptanalysis. We choose in which direction I want to change the input. And I'm going to watch what is the effect on the output. If I wiggle it in the direction where the ReLU was negative, the wiggling is going to be stopped by the ReLU. I'm moving from 0 to minus 0.1, and therefore the output remains the same. If I'm wiggling towards the positive side, I expect to see a strong wiggle in the output. Details are complicated, I'm running out of time, so let me just tell you. So this tells you in which direction you want to wiggle. It's a statistical test. So when we actually applied it to the network with 8 layers, with 2048 neurons, so for neuron number 0 in the 7th layer, we ran 200 experiments to see which one of the wiggles on the two possible sides was bigger. So the real sign was minus. 165 out of the 200 experiments suggested minus as the sign. 35 suggested plus. I take the majority. And in the second neuron, there were 0 votes for the wrong sign, 200 for the correct one. As you see, it is very strongly biased, and therefore we got the correct signs everywhere. Okay, I'll stop here. There was another technique based on second-order differential cryptanalysis. I'll not talk about it. So, as you see, in 30 minutes, we managed to solve a problem which the best previous technique would have required 2 to the 256 in order to exhaustively search through all the possible sign combinations. Thank you very much.
Thank you very much, Adi, for this very interesting talk. So we can ask your question.
Hi, thanks for the talk. I was wondering, why did you choose to submit to Eurocrypt rather than Eurocrypt, where you might reach more of the clients that might be trying to protect the weights?
I think that the Eurocrypt is a problematic conference. The results of submissions is a coin toss. And I don't think they would actually appreciate a paper which doesn't improve the state of the art by 0.1% from 78.5 to 78.4.
I see. So you think there would be no years on that side, so to say?
I'm afraid not.
Thanks.
Hi, thanks for the really interesting work. Just curious if you have any thoughts about countermeasures that won't degrade the utility of the models too much.
We thought that there is a countermeasure, and in the last few days, actually, we are working on countermeasure, which overcomes the countermeasure. So until this settles down, I will not tell you.
Thanks for the very interesting talk. Because I was working on something related to machine learning security and privacy, I would like to ask about the motivation, because there are also works like in the security venue or maybe in the machine learning conferences where people do the black box model extraction using a similar strategy like training another deep learning model or something else, which actually achieves the same functionality as what we did.
No, it's an approximation of the functionality. I find the exact weights. I find the weight with infinite precision. If you just train the new network, first of all, it will cost you roughly the same as, forget about the original model. Don't try to steal it. Just train your own model at the same cost, and you get it. And on top of it, the two models are going to be roughly the same, but not exactly the same.
Okay, so from my understanding, and this is much, much more severe attack against the model itself instead of like those model extraction stuff or model stealing attacks. I see, thank you.
Okay.
Thank you for the very nice talk. I was wondering if you can come back to your comparison between DNNs and the design of block ciphers.
Yes.
Do you think there might be some dual insights that you can get there as a cryptographic designer from techniques from the DNN literature, or not so much?
So I pointed out that we are using, for example, second-order differential attacks, and we are using layer-by-layer attack, and we are using a carefully chosen direction to perturb the input in order to maximize the effect. So we have been using a bag of tricks that had been developed over the last 30 years in cryptanalysis. We certainly
yeah, I was wondering the other way around, like some ideas that came from the DNN literature might be useful to design better block ciphers, for example.
No, in that direction I didn't see that, unfortunately. Yes.
Thank you for the great talk and also the great font choice. My question is about, will the work apply to activation layers that's not ReLU? Because you mentioned that,
yes.
For example, you're using like the ReLU layer blocks something then.
Great question. I'm actually using the fact that there is a sharp bend in the ReLU. We could easily extend it to leaky ReLU, for example, in which the negative side doesn't have a slope of 0, but has a slope, say, of 10%. The same attack will be applicable. We cannot apply our technique to a sigmoid-like activation function because the sigmoid is kind of smooth. I don't see any sharp bend, and therefore it's an open problem, and you're all invited to think about how to extract the parameters in a sigmoid-based scheme.
I see. Thank you.
Okay, a very short question, and this is the last one. We are already late.
Thank you for the talk. The question is, forgive my ignorance of neural networks, but my understanding is for many of these, the input is actually somewhat discrete. I mean, if you input a digital picture, you have, you can flip a bit, but that's going to have some non-smooth, non-continuous difference on the input. So your technique seems to depend on very, very tiny differences in the inputs.
Right.
Yeah, so I understand how does that work, or how does in practice?
Okay, so it does not apply to situation in which each one of the inputs has very limited accuracy. If the input is 64-bit accuracy, then as I said before, we could detect realistic networks with 64-bit of accuracy. But if each one of the inputs was allowed to be only 0 or 1, I agree, I will not be able to apply our technique. It has its limitations.
Okay, well, thank you.
So thank you. Let's thank the speaker again. So the second talk of this session is about new results against the hash function SHA-2, and the talk will be given by Ying-Xin Li. Yeah, the slides with it's okay.
I'm going to present our work new record in cleansing attacks on SHA-2. My name is Ying-Xin Li. This talk will be divided into 3 parts. And the first part we will briefly review SHA-2. SHA-2 family is a population hash function, is a series of hash function standardized by NIST. And the SHA-2 is to strengthen the security of SHA-1, which have a more complex compression function. And the SHA-2 mainly consists of two versions, namely SHA-256 and SHA-512. SHA-2 has been used worldwide, especially SHA-256 is used in Bitcoin. The SHA-256 and the SHA-512 all share almost the same step function and the message expansion. So I take the SHA-256 as an example to explain the compression function. And the compression function of SHA-256 mainly consists of step function and the message expansion. In the step function, the EI is updated by the EI-1, EI-2, EI-3, EI-4, EI-4, KI, and the WI. The AI is updated by the AI-1, AI-2, AI-3, AI-4, and the EI. In the step function, the blink function sigma 1, sigma 0, sigma 1 if and mj are given by these 4 equations. In the message expansion of SHA-256 splits the two 1-bit message block mg into 16 words. I is between 0 and 15, and expands them into 64 expanded message word wi. If the I is is between 0 and 15. The WI is MI, and the I is 16 and 33. WI is updated by the WI-2, WI-7, WI-15, and WI-60. The blink in the message expansion, the blink function sigma 0 and sigma I are given by these two equations. In the second part, we will introduce free star, semi-free star, and clean attacks on SHA-2. Finding a value attack requires attacks to finish the following three tasks. Task 1, select the message difference to construct a local collision. Task 2, search for corresponding differential trail in WI, AI, and EI. Task 3, find a conforming message pair to verify the differential trail. Then our contribution is task 2. We can use a set SMT-based method to solve task 2. It can be exciting to over the state of the art. I will show you the first result on SHA-256. Also there is a practical semi-free star. Clean attacks on 39 steps SHA-512. A similar attack on SHA-256 cannot reach 39 steps. So we believe the main reason is that the exciting tool cannot find a valid differential trail for 39 steps SHA-256. However, with our tool, we can find it and give a practical collision on 39 steps SHA-256. As in the semi-free star clean attacks on 39 steps SHA-256, we choose to inject the non-zero message difference at W8, W9, W11, and W16, W17, W24, and 26. In this way, we can construct the local collision as shown in this figure. As the first steps, search for the 39 steps differential trail. Our goal is to minimize the Hamming weight of the sign difference WI, and which means we also want to keep the differential trail in WI as sparse as possible. And we also want the minimal value of sign difference WI. But we did not fix the concrete of solution of the sign of the minimum value of sign difference TW leading to this minimum value. And the second steps, we minimize the Hamming weight of the sign difference data AI and the conditions that modular difference A19 to modular difference 38 are 0. And the module difference E23 to module difference 2038 are 0, and the sum of the Hamming weight of the sign difference data WI is TW. Finding the minimum value of TA such that there exists a solution. The TA defines the sum of the Hamming weight of the sign difference delta AI. Still, we only aim at the minimal value TA, and we do not affect the sign difference WI, sign difference AI, and the sign difference EI. As the third step to search for the 39 steps differential trail, we minimize the Hamming weight of the delta EI in addition to the condition at step 2. We further add the condition, the sum of the Hamming weight of the sign difference delta AI is TA, and those conditions found out of the solution of sign difference delta WI, sign difference delta AI, and the sign difference delta EI that minimize the sum of the Hamming weight of the sign difference EI. So we have found the 39 steps. We can find the 39 steps differential trail as shown in this figure. But it is unclear. It is unclear whether it is valid or not. So we need to find a conforming message pair for this differential trail in order to show it is correct. We extract all the constraints on WI, AI, EI for this differential trail, and we add those constraints to the set SMT model for the volume transition of SHA-256. Then if the model outputs the solution, we can easily to get a Canadian message pair M and M prime, and we give the practical semi-free star cleaner attacks on 39 steps SHA-256. And the second way we can show the other results on SHA-2, and the first practical free star cleaner for 40 steps SHA-224. The SHA-224 is the truncated version of SHA-256. The last output was of the SHA-256 one was truncated. We inject the difference in E-4 and W0, W9, W10, W11, W13, W17, W18, and W25 and 27 to mount a free star cleaner attack. The searching strategy is almost the same as the 39 steps SHA-256, and we can get the 40 steps SHA-224 differential trail. Based on the 40 steps differential trail with the similar technique to model the volume transition, we can easily to get the free star cleaning message pair M prime, as shown in this figure. And then we introduce our new attacks on 39 steps SHA-512. Currently the best cleansing attacks on SHA-512 only reach 27 steps, and but the best cleansing attack on SHA-256 can reach 31 steps. So this is a gap. We believe the main reason is that the existing tool cannot find a valid differential trail. So I wonder whether it is possible to use our new tool to find such a differential trail. So we do this in this way. We minimize the handling with of the sign difference data WI. And the second, we minimize the handling width of the data AI, and we minimize the handling width of the data EI. Following this procedure, we can find a 39 steps differential trail, but we found that this differential is invalid, so we need to make it valid. And the first, we set the sign difference E5 and sign difference E6 and sign difference E7 as unknown variable. For remaining sign difference EI, where I is not, 5, 6, 7 keep them the same as those in the obtained solution. For the AI and for the sign difference AI and the sign difference WI, they can also keep the same as those in the obtained solution. And then we add the constraints describing the value transition for AI and WI to the model. And then we can find, in Word, we utilize the degree freedom in sign differences data EI and the model for value transition to correct an invalid 31-step differential. We have found the 31 steps. We found a valid 31-step differential trail. To demonstrate that the 31 steps differential trail is valid, we provide a 31 steps semi-free stack-leading message pair. We showing the other results on chart. We can give a valid 28 steps differential trail for SHA-512, and based on this differential, we can give the leading message pair for 20 message pair for 28 steps of SHA-512 for the first time, and then I also mentioned that we can improve 31 steps differential trail for SHA-256 with fair and control condition, which help improve clean attacks on SHA-1 steps, 31 steps SHA-256, and this is a summary. Thank you for listening.
Thank you for your talk. Please come to the mic if you have any question. Okay, so a quick question. Would it be possible to apply the result of this paper to improve the attack against SHA-1?
I want to try some, but it's shown bad. Its result is not good.
Okay, thank you.
Thank you.
So, please thank the speaker again. So the last talk of this session is partial sums meet FFT, improved attack against 6-round AES. Please give your talk, Shivam.
So we'll discuss about improved attack on AES. Using two previous techniques, we mix them and get some better attack. So let's see, this is, if I first motivate you why we need this, then two previous attack on AES, then we show that how to improve that attack. Okay. So from a cryptanalysis perspective, we try to do two parts. At first, we try to find some distinguisher, and then we try to do key recovery. Now, searching for distinguisher is a part of research direction, but our today's focus mostly on key recovery. We know this distinguisher, we want to do key recovery for it. Okay, so let's see a very basic example of a cipher. We have a E and F inverse. We try to find we have a distinguisher for E, and we try to find key recovery attack on F inverse. So basically what we do, so this is a, first of all, chosen plaintext attack. We have a set of plaintext that adversary can choose as he will. So we consider a structured set of plaintext maybe from a P, and we get the ciphertext. Now we try to use this for key recovery. So suppose we have some property here at the position of chi. So for example, this property can be anything. In this talk, we mostly focus on integral or zero-sum distinguisher. So this property is sum of all the elements at the position of chi is to 0. So you know this thing with certainty. Can you use this to find the key? That is k. So basically, the basic idea is that if you choose that k, for the correct key, if you go back and check the sum, it should be 0. So this is the kind of thing that separate that E function from a random function, and you try to use that property to recover key. Now, let's try to think how to recover this key. Let's try to do this from a programmatic point of view. So this function foo, compute this. You have a set of ciphertext, you choose all possible k, and go through all possible c, and compute this sum. If sum is not equal to 0, you discard this k. Now let's see this function bar. This do the same thing. So basically, when you compute that sum, its sum is not equal to 0, but we don't need to, that sum is over XOR. So you just need the even or odd occurrences of the sum, not the exact result. So we can do this in the same way in this function. So you just take even or odd occurrences here of the C. If it is occur even number of times, you don't need to consider C. So in a sense, foo and bar, there's an equivalent. But you can see that this bar is basically computing convolution for each k. Now, this convolution is basically a matrix multiplier. This is a very small example of this. So basically for each k, for example, for k equal to 0, you compute that, you multiply that vector with that vector. And this you get from the ciphertext. Now, let's focus on a particular property of this matrix. So this matrix is blockwise cyclic. If you see all 2 cross 2 block, those are cyclic, like this. Also, if you see this, now you take 2 cross 2 matrix as a single block, this is also cyclic. Similarly, this. Now, this kind of matrix has a specific property. Basically, these are diagonalizable with respect to the Habermas matrix. Now, what is Habermas matrix? It's basically ijth element is -1 to the power I into j. For example, this one, or in general, this. Now, computing matrix vector multiplication when the matrix is a Habermas matrix, you have a very nice algorithm, first Habermas transform basically. It's a divide conquer algorithm. You can do this with m2 to the power m complexity. Now, let's get back to the foo and bar. So in that case, in the bar algorithm, we basically try to multiply a matrix with a vector. Now, instead of multiplying directly, you can just diagonalize it, then multiply it. Now, when we diagonalize, we have to focus what is the element of these diagonal elements. So here, the diagonal elements can also be computed using a Habermas transformation. Basically, you take the first column of this matrix, you multiply with the Habermas matrix, you get the delta, that is diagonal elements. So basically, multiplying this matrix vector, it can be transferred to 3 Habermas transformation and one vector-wise multiplication. So complexity reduced to 4m2 to the power m. For example, for m equal to 32, it's reduced to the power 64 to 2 to the power 39 using this technique. So now let's discuss the integral attack on AES. So this is the integral attack. So basically, you take a particular type of plain text at the starting, mainly 2 to the power 32 elements at the diagonal. And here, you get a distinguisher. Basically, if you sum them, you get 0. So you try to use it to recover keys from 5th round and 4th round. I mean 6th round and 5th round. So to do this, you take 4 bytes of key from 6th round, 1 byte from 5th round, and you do the key recovery. Naively, it has complexity C into 2 to the power 72. The C is basically, the filter size is only 8-bit, so you need multiple delta sets or multiple structure set to do the complete recovery. Now, Todo proposed in 2014 about using FHT or FFT to recover this step. So basically, when you do FHT, you have this type of function. Now, if you fix this K4, then you get exactly 32-bit K and 32-bit C, and you try to apply FHT that I show you, basically the bar algorithm, to recover this key. Now, there is one problem with finite field arithmetic is that the FFT or FHT algorithm works over integer field, not over finite field. But you need result in GF2 to the power 8. So basically, you separate, so you have an 8-bit function, you compute 1 bit at a time. So you have to apply the bar algorithm 8 times. So here is the idea, and you compute convolution for each FI separately. So if you see the complexity is C into 2 to the power 8, around 2 to the power 50, and you have memory complexity F into 2 to the power 32. Now, let's see another attack strategy that discovered more than 20 years ago, the partial sum technique. So basically, in the partial sum technique, what you do, you have to compute this function for all possible K, all possible C. Instead of computing at a time, you compute part by part. First compute this part, store the result, then compute the second part, and so on. So basically, this is the basic algorithm. So basically, here, you take which ciphertext occur even or number times, and you choose 2 value of K0 and compute the result in A1. So this is the first part. You reduce that function to this function, and you have to pay complexity up to the power 48. So at a glance, you can do like this. You compute the first part, then you compute the second part, third part, and each step has to the power 48 complexity. So the around complexity is C into 2 to the power 50. So this is the previous 2 technique. Now we will try to merge them to get a better attack. So our basic idea is that we follow the general structure of partial sum technique. We replace each of the partial sum with FFT. And we rearrange the steps to make it FFT compatible. And finally, we rearrange the step again to reduce the memory complexity. So let's see the idea. So again, this is the picture. We want to compute this part. So let's do this part. To compute this part, we have to compute a value of A1. We take this A1, we put it in the partial sum thing, and this is the convolution part. So we are doing the same thing as a partial sum technique, but using FFT. Similarly, if you can see to do the second part, we previously we compute convolution for each K0, K1. Now we have to choose a K0, K1 and go for the next step, and so on. So this is how you go one by one, and you compute. So basically, I'm just replacing each step of partial sum using a FFT. And if you replace each of these steps using partial sum, using FFT, each time you gain some complexity. So basically, we reach at 2 to the power 48.5. But we need 2 to the power 40 memory, because at the starting, we have all possible 2 to the power 24 size array for all possible keys. Now, there is one important thing is that this last step is computing the maximum number of time. And here I discussed before that this S function, there we are computing over XOR, but FFT not applicable over XOR. You have to compute over integer domain. So the fact is, according to Todo's algorithm, we have to do last part 8 times. But we say that, let's assume we are computing this thing in a 64-bit operation. So computing one FFT at a time is basically a waste of resources. So what we do, we compute several multiple FFT in a single 64-bit register so that we can use the parallelism. So the idea is this. So suppose you have a 64-bit register, and you give 7 bits for each partial sum. Now, there are 2 risks. One is this computation will affect this bit, or maybe there will be an overflow. So to tackle this, we need to see how we are computing partial sum. We are computing FFT over a vector. So we have to see how this vector, elements of this vector is distributed. So basically, how large this B should be, so that this computation never overflow in each bit. So it never overflow here. And we see that these elements are basically, this S is a balanced function, and these elements are 128 elements. So basically, this is a binary distribution with probability half-half. And the expectation is 64, and standard deviation is 4√2. So using Chernoff bound, you can easily find that if you take B equal to 7, this probability is extremely low. So the overflow probability. Now, B is too large, then we can overflow at the end. Obviously, we don't consider we need only 1 bit. We don't consider the overflow beyond 64-bit. But assuming each of these less than 2 to the power b, there will be no overflow if 7b less than this. So these 2 conditions satisfy together when you take b less equal to 7. And using b less equal to 7, only at the last part, and we gain some complexity. But when we achieve this idea, we say that why don't use multiple parallel thing in the other parts as well? Though we are computing FFT of size 2 to the power 16, but still we can gain something. And we say that using b equal to 7 there as well, with very less error rate, we can compute this attack. So basically the complexity becomes 2 to the power 45 versus 2 to the power 48. So here is the improvement graph, but we still need 128 GB memory. To reduce memory, we divide the first part again in 2 parts. So basically, in the partial sum, if you divide first part in 2 parts, then basically you have to pay more complexity. But the gain is much better here because you need low memory access. The attack is much faster than the previous attack. So here we are gaining 2 to the power 646 and 0.5 GB of memory, basically. So let's conclude. So we implemented all of our attacks in AWS instances. We choose the instances which is best for a particular attack. For example, in some attack you need more memory. In some attack you need more threads. So basically we show that our attack is 65 times faster than previous attacks and at least 83 times cheaper. Basically with 5 USD you can attack 6 round AES. Also, we did other multiple improvements, like some FFTs you can pre-compute. That is one thing. And also, we say that, so we have multiple for loops, but the last for loops computing most of the times. Now, when you filter with one delta set, one set of data, for the next set, there are very few elements which computing the for loop. So there is no point to compute the whole FFT again. So you can improve that at this point. And finally, we reach at the complexity of 2 to the power 46.4. And this is the complexity of the low memory algorithm. We apply this technique to other cipher as well, like Kuzniaczek, Misty, and Clefia, and we get significant improvement. And all these codes are available here in GitHub, and will be in ISR archive in few days. And thank you.
Thank you, Shibam, for this interesting talk. Is there any question? I have one question. I know the partial sum technique also applies against 7 AES rounds.
Yes.
try to apply your technique against 7 rounds? Do you have a gain? Because
Yes, but we did not gain that much, I guess. We did not gain that much, but this technique is quite general to partial sum. I mean, where you can apply partial sum, you can apply this technique, but it depends on how much you are gaining in each step.
okay, understand. And I think the partial sum can also be performed in parallel using a 64-bit.
Exactly. So
how efficient is your implementation of the partial sum?
okay, so basically I was expecting this question. I have few other slides for that. Okay. So suppose I am using other attacks as well as packing. Now you can, so basically in packing techniques, you are computing multiple FFTs in a single register. Now you cannot compare this parallelism with SBox access, but even if we access SBox parallelly, then finally we consider that suppose there is one addition is equivalent to 16 SBox access. Then also we gain 60 times improvement than partial sum. And if you use Todo's attack and try to, in Todo's attack you can at most pack 2 FFTs because it's a 32-bit FFT computation. Then our gain is 20 times.
Okay, thank you very much. So please thanks Shibam again and all the speakers of the session.